Hi there, so this is Team 1's TPMS MATLAB simulation implementation. So I'm going to be going into detail line by line of how the end-to-end implementation works, and then go over some of the results. As you can see, so starting at the top, we have a bunch of parameters for sample rate, samples per symbol, the frame size, number of frames. Number of frames is kind of irrelevant for this. We're just doing one frame for this example. The modulation order for the FSK modulation scheme that we're using. And then the frequency stepping, so how much per symbol the modulator steps over from the center frequency. And then we have a parameter for frequency offset, because this generates a frequency offset and then corrects. Has a phase offset, it's not used right now. And then has impairments for noise. We're implementing AWGN. It's also a timing offset that was taken from Lab 1. And then getting down into the data, we have the actual packet that's used. So this is manually constructed, starting with a preamble. The preamble is smaller than what it really is. It's just easier to type less, I guess. But once we determine what the preamble is, through correlation in actual implementation, we can paste the correct preamble. And then following that, we have the actual data. So starting with pressure, that's implemented as just like random ones. So it's a bunch of ones for now. Temperatures, half ones, half zeros. The TPMS ID is just random values I chose, flags, and then a CRC. And then that's all put together into a vector and then fed into an FSK modulator using the parameters defined above. And then we have a TX filter, so a raise cosine transmitting filter, a raise cosine receive filter. We have our noise generation, variable delay, and then some the spectrum analyzer, so we can view the spectrum because that's really useful, and then a time domain scope, so you can see the actual different frequency changing. And then we get into the meat of it, so normalizing an offset based off the sample rate, so that we can actually get a defined frequency offset based off a set sample rate. And then we go through, we first put our modulated data through the transmit filter, we add noise to it, we offset it and put a timing delay in it, and then after that a frequency shift is added, and then the data is brought back into the receive filter. It's not actually using a symbol synchronizer. The synchronizer still needs to be worked out, where it actually outputs less than the expected received data, and that doesn't play well with the frequency demodulator. So we'll have to work on that a little bit later. Then we display with the spectrum analyzer the receive signal, display with the time domain plot. You can see the differences. And then the code waits, so we can go over that when we run the code. And then the next part is actually correcting for frequency offset. So the scopes will allow us to see, at least the spectrum analyzer will allow us to see the frequency offset before it's corrected. This calculates the frequency offset and then corrects it. So it finds, because we're using two symbol, it finds the two max frequencies present. So it takes an FFT and finds the 2 points along the spectrum where the maximum amplitude is present. Then we take those two frequencies and find the average, the middle between them, and then that is subtracted using a complex exponential. So the data is actually shifted over that amount, the center frequency, and then that data is displayed again using the same spectrum analyzer. The data is demodulated, and then a graph of the received and transmitted data is shown, as well as the bit error rate is calculated. So if we go ahead and run this, I'll give it a little second. First, we'll see the time domain and spectrum analyzer. So center frequency, we're expecting our signal to be right here. It is in fact just over 30 kilohertz off center. This will definitely not be able to be decoded. And if we look at a time domain plot, we can actually see the frequency shift keying. And then this plot will stay here, and I'll be able to actually show against the data. But you can see there's some low frequency, high frequency, low frequency, high frequency, and so on, so on. So you can actually visualize in time domain FSK. So if I tell it to move on, this is the corrected signal. As you can see, there is no longer a frequency offset, and it is centered around the received signal. If I continue on one more, we'll get a graph with the transmitted and received data. And if you line those up, they are in fact matching, and that's good because we have a very high signal to noise ratio right now, and the bit error analysis, or the bit error rate, is 0 as expected. Now you can actually compare that with the time domain. You can actually compare that with the time domain, so you can just see the start of low frequency and then a single value of high frequency and then a bunch of low frequency, a couple more high frequency. So you see the data matches up in the time domain. Now if we were to add a little more noise to the system, say reduce it down to 10 and run it again. If you look in the offset data, it is calculated to be around 32 kilohertz. So that's right on the money. So you can see our time domain scope is much harder to read. In fact, it's pretty much impossible by eye to actually see it visually. And then our spectrum analyzer shows much higher level of noise, but there's still a peak, so the frequency compensation should still work. And if we push the simulation forward, it does indeed find the same offset value, and it does still decode it, except looks like there's just one error between received and transmitted, and yes, it's right there. So with a bunch more noise added, it does in fact receive or have a bit error, and this would be taken care of by the CRC. The CRC would calculate its own CRC based off of all of this data, maybe not including the preamble, depending on the manufacturer. And then you'd compare your calculated CRC against the received CRC, and in fact they wouldn't match, and you would have a invalid packet. So that's pretty much the demo.